Welcome back to CSConnect series. We are actually in data representation. Last video was dedicated to various binary codes. In this video, we will see one of the binary codes called error detection codes. So let me describe you a scenario. There are two systems. When there is a transfer of information between these two systems, it happens in binary form. Let's take this to be system X and this to be system Y. And there is a channel involved in it. This channel is a physical system. In the sense, it can be any cable or any other new technology that is actually transmitting information. This channel is actually a physical system. Physical system will always have some noise associated to it. What are noise? Noise are not some kinds of sound, but noise can be taken for some kinds of disturbances or obstacles. Say for example, in a cable, if you find a cable damaged in between, it's a kind of noise. So when there is a noise in the physical system, the sent information may not be equal to the received information. When a transmission occurs, how can we confirm that the sent code will be equal to the received code? In order to use the term code, I have mentioned here as binary information. So how do we check this? An error detection code can be used to detect error during transmission. What can we do with that error detection code? So the presence of error will be indicated with that code, and we can observe the frequency of errors. For these two things only they have been using error detection codes. On observing the frequency of errors, if you find the error occurs only once in a while, all you can do is you can retransmit the information. So the message is transmitted again. Say for example, X is transferring something to Y and you find 10 is received as 01. This transmission error is happening once in a while, you can send it again. What happens when this error occurs frequently? We have to check whether the physical system is functioning properly. The system is checked for malfunction. So if the channel has some problem in it, you will have more and more errors generating. If you take, there are 10 transmissions happening. Out of that, 9 are going to be with error. Then you can obviously say that there is a problem in the physical system. But out of 10, if 9 are going to reach correctly, one might have some problem in the mid. You can transmit that one again. So whether you are going to transmit it once again or whether the system is going to be checked for some malfunctioning, everything depends on the frequency of errors. So at least for this purpose, we need some code, and that is what we call as error detection code. So in this error detection code, we are going to see the concept of parity bit. This concept is having a heavy place in networks. What is a parity bit? It's an extra bit included to make the total number of ones either odd or even. How do we actually do that? Let's take a message. What is this message actually? This is the decimal number represented in binary from 0 to 15. The message is having 4 bits and the parity bit will be 1 bit because they have mentioned here as extra bit. This message will attach the parity bit along with it and it will be sent to the receiver. So if this is going to be X and this is going to be Y, if X is going to send some M, along with this P, it will be reaching the receiver. Based on this P, the receiver will decide whether the message is right or not. This is the actual case. So the message is going to be 4 bits. The parity bit will be 1 bit, which makes it totally 5 bits. So when sender is sending 4 bits, receiver will get 5 bits totally. There are actually two kinds of bits involved. One will be the odd parity bit and the other will be the even parity bit. What is odd parity bit? P is chosen such that the sum of all ones, all the 5 bits together is odd. So let's take the odd parity here. Now the message has 4 zeros. There are no ones. We can say there are 0 ones. 0 is also even. When there is a message with odd number of ones, in P of odd, we place a 0 to retain the odd number. If the message has even number of ones, we add 1 in the parity bit to make the count as odd. Say for example, if there are 3 ones here, a 0 will be added to keep those 3 odd number of ones as odd. In case if there are two number of ones, an extra one is added to make it totally three numbers of ones. This is the concept of using parity bit. Now here there are no ones. No ones means 0 ones, as I said. 0 in the sense it is even. When it is even, what is the odd parity bit that is added? It is 1. When I add 1 here, the message becomes 0 0 0 0 1. Now how many number of ones does this have? It has only one number, which is odd. Now let's take the second number. We have only one here. So it is already odd. If it is already odd, what will we add here? We will add 0 bit here. So this will be 3 zeros and 1. The fifth bit will be 0 here. So the fifth bit is the parity bit added here. Now let's take randomly 1 0 0 1. How many number of ones are here? There are two ones, which is even. When it is even, in the case of odd, you have to add another one to make it odd. The ultimate aim of adding odd parity is to make the message have odd number of ones. That's why when there is even number of ones, you add another one to make it odd. When there are already odd number of ones, you just add a 0 to retain those odd number of ones. Now let's check 4 ones, 15. There are even number of ones, so we are adding 1 here to make it odd together. Along with this, if you count 4 ones and another 1, this will be 5 ones. Now the count of 1 will be odd. Now let's take 1 0 1 1. There are 3 number of ones, which is already odd. So we are just adding a 0. This is the concept of odd. What about even parity? P is chosen such that sum of all ones, all the 5 bits, is even. Wherever you represented 1 in odd parity, this will be turning to 0. When the message has even number of ones, you are not going to disturb it, you will just add 0 to it. When it has odd number of ones, we add 1 in order to make it even. When you add odd plus 1, this becomes even. This is the concept. Say for example, if there are 3 ones, if you add another 1, this will be 4 ones, which is even. Now let's take the first one. 4 zeros is already even, so we are placing a 0 bit here. Let's take 4 ones. It is already even here, so we are placing a 0 bit here. What about 3 ones here? You are placing a 1 bit to make it even. It will be 0 triple 1 and the fourth one is the parity bit. Now how this parity bit is generated? We'll again see a scenario here. We have the sender and the receiver here. The sender is having a 4-bit message. This message is sent to the parity generation network. Here the parity P is generated. Based on the count of ones it is generated, the message along with the parity bit is sent to the parity check network that is present on the receiver side. That's why generation is placed under sender and check is placed under receiver. In this parity check network, we are checking whether proper P is adopted. If the parity is telling there is no error, the 4-bit message will be taken as correct by the receiver. How does it know if an error occurs? An error is detected if the checked parity does not correspond to adopted one. So based on the parity bit, it will be decided whether the message is received right or wrong. What kinds of error does it detect? It detects the presence of 1, 3 or any odd combination of errors. Then what will happen to even combination of errors? Even combination of errors is undetectable. So let's get into practice problems of error detection code. List the 10 BCD digits with an even parity in the leftmost position. Totally there should be 5 bits. So 10 BCD digits will have 4 bits and the parity will be 1 bit. So totally 5 bits per digit. Repeat with an odd parity bit. So first we have to do this with even parity and then we have to repeat the same 10 digits with odd parity. Let's start. If you take, this is the BCD code, the 4-bit code. This is the leftmost position and this is the rightmost position. Usually parity will be added after the message only. Here they are asking us to add it in the leftmost position. It means they are asking us to add in front. So let's take the BCD digits. We'll take from 0 to 9 because they are asking us to list only 10 digits. Now we have to find the even parity bit. There are even number of ones here. There are no ones, which means there are 0 number of ones. So there are 0 ones. Here there is 1, 1. Here there is only 1, 1. Here there are 2 ones. Here there is only 1, 1. And 2 number of ones are here. 2 number of ones here. 3 number of ones here. 1 number of 1 and 2 number of ones. Wherever you find even number, here, in these 5 positions, you will have 0. In the odd positions, you will have 1. In 0, 2, 2, 2 and 2 you have 0 because you are retaining the even count. Wherever you have odd count, you are introducing an even parity bit 1 in order to make the total count as even. So how do we write this? We have to write the parity first because they are asking us to write it in the leftmost position. Along with that we will write the BCD digits. Next the 1. Along with that we have to write the BCD digits. Then 1, 0, 0, 1, 0, 0, 0, 0, 1, 1, 1, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1, 0, 0, 0, 0, 1, 0, 0, 1. Now just count and see. There are even number of ones here, that is there are no ones here. There are 2 ones, 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 there are 4 ones, there are 2 ones and there are 2 ones. All the 5-bit messages are having even number of ones. This is the ultimate goal of adding even parity. Now we have to repeat this exercise using odd parity bit. So let's take the BCD digits. 1, 2, 4, 7 and 8. These are the places where we have odd number of ones. So straight to that we will have 0 because we are going to add odd parity here. And the rest of the places will have 1 in order to make it odd. Now how will we write odd parity with BCD? 1, 4 zeros, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. So the first bit is the parity. The next 4 bits are from BCD. 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 0, 0, 0, triple 1, 0, 1, triple 0, 1, 1, 0, 0, 1. Now count all the 10 digits, you will have odd number of ones. When they ask you to add parity bit, just confirm whether it is odd or even and then confirm the position whether you have to add in left or right. If it is not mentioned about the position, you have to add it this side only. When they have explicitly mentioned in leftmost position or in the most significant bit. So this is the most significant bit and this is the least significant bit. When they say left or MSB, most significant bit, you have to add it first and then write the corresponding 4-bit message. If they have not mentioned anything explicitly, always add the parity bit in the right side. That is in the least significant bit place. The next problem. Determine the odd parity bit generated when the message consists of the 10 decimal digits in the 84 minus 2 minus 1 code. We have to find the 84 minus 2 minus 1 code. How do we write 0? We'll add here 4 zeros. And the question is about odd parity bit. Then we have to write 1. How do we write 1? 4 minus 2 is 2. 2 minus 1 is 1. So we'll have 3 ones here and a 0 here. Then for 2, 4 minus 2 is 2. The remaining places are 0. For 3, 4 minus 1 is 3. The remaining places are 0. In order to give you clarity only, I have divided the weights in different columns and I am correspondingly writing the zeros and ones. 4 will have 1 and the rest of the places are 0. For 5, we have to take 8 minus 2 minus 1. This will be 0. For 6, it is 8 minus 2. So this is 4 minus 2. This is 4 minus 1. For 7, it is 8 minus 1. For 8, it is just 8. For 9, 8 plus 4 is equal to 12. 12 minus 3 will give 9. So all the places will be 1. How many ones are here? 0 ones are here. 3 ones are here. 2 ones are here. 2 ones, only 1 1. Then 3 ones, 2 ones, 2 ones, only 1 and 4 ones. Now we have to determine the odd parity. For odd, when you find odd number of ones, you have to add 0. When you find even number of ones, you have to add 1. Here we have even number of 1. It means a 0 count. So the parity bit is 1. 3, it is odd. It means you have to use 0. 2 is even. So we are using 1. 2 is even. We are using 1. 1 is odd. So we are using 0. 3 is odd. We are using 0. 2 is even, we are writing 1. 2 is even, we are writing 1. 1 is odd, we are writing 0. 4 is even, so we are writing 1. Now if you take the message parity, 4 zeros and a 1 together are taken. The message will be written first and the parity will be written next. Since they have not mentioned anything about where it has to be mentioned, we are writing in the usual order. 1 is having 0 triple 1 and 0. Then we have 0 double 1 0 with a 1. Then 0 1 0 1 with another 1. 0 1 0 0 with a 0. 1 0 1 1 with a 0. 1 0 1 0 with 1. 1 double 0 1 with 1. 1 triple 0 with 0. 4 ones with a 1. Just count, you have odd number here. It is 1. It is 3. It is 3. It is 3. It is 1. It is 3, it is 3, it is 3, it is 1 and it is 5. So there are odd number of ones in the message plus parity. So this is the odd parity bit that we have to determine. This is just an introduction about error detection codes. I just want to introduce you to error detection code so that it will be useful when we are seeing networks related topics. I'll meet you in the next video. Thank you viewers.